scientific reviews. For example, if it goes through a review when you're submitting a protocol to be funded by the NIH, there's a peer review and scientific review that reviews that protocol. There are also other medical centers like the Georgetown, we have Lombardi Cancer Center, and we have our own cancer scientific review. And they will review it and make sure everything is ethical before it moves on to the IRB. And then after that, there's also a data and safety monitoring board. So that when the study is going, you want to make sure that somebody is monitoring, how it's doing. And even, especially if it's being done in a blinded fashion, because if everybody who's getting the treatment is living much longer and everyone on the placebo is dying, they may unblind it and end up treating everyone. So there may be early stopping rules that your data safety monitoring board will go by to determine if the drug is a benefit or if it's detrimental. If they find that everyone on the treatment arm is ending up with liver toxicity, they may terminate the study prematurely. And of course, most recently, there's genetic testing that's going to be done that has to be added to the consent. And today, we store a lot of blood samples, and people will go back to them later in time and do some GWAS studies or RNA-seq, and are looking for some genetic alteration. If blood samples or tissue samples are going to be stored, there has to be included in the consent form a paragraph about the risks and benefits of that. Because if you discover that this patient has a hereditary, SNP that may worsen their long-term survival, and if insurance companies find out about that, they could lose insurance. So all those things need to be stated upfront in the consent form so that patients are aware, and they can elect to have their samples removed and not kept in storage with the new genetic codes. So how do you do it? What are the nuts and bolts? And I'll just give you some examples from my experience and some studies that I've done. First of all, it takes a whole research team, and that's very important. No man is an island anymore. There's going to be the principal investigator, there's co-investigators, but there are other very, very important key players that will help the study be successful. One of those is the nurse or the study coordinator, who will make sure that all the documents and the patients are taken care of properly. Having a statistician is extremely important, so they tell you your sample size, and then they'll crunch your data when you're done. I had one study that had over 100 patients in it, and I just handed the Excel file with the data in it over to the statistician, and they did all the analysis. And it's actually better that way, because you don't want the person who's in charge of the study doing the analysis. That way it is, not biased to one group versus the other. And the statisticians usually don't know which is the treatment group, because they're group A and group B. So that makes it a much more rigid study. You should have a data manager, and whenever they're entering the data manager may not know what the normal range is for, say, an ALT and the liver enzyme. So usually we have a place in our Excel files if they're entering something and it falls outside the range, or they're entering a wrong number by mistake, it'll pop up red. So there are a lot of ways to keep a foolproof so that they don't enter some data in error. And of course, we talked about the data safety monitoring board. You have to have an investigational pharmacist, because when this is done in a blinded fashion, the only one who really knows what the patient's getting is the pharmacist. And if there's a problem and you have to unblind the study, it's the pharmacist who knows what they're taking. So before you start the trial, there's several things you need to do. First of all, you can't do a clinical trial with a drug or a device in humans without approval from the Food and Drug Administration. And so you have to apply for an IND or investigational new drug number. And I can show you an example of the 1571 form that I have here. Then you also have to write the protocol, and that's the study design and what you plan to do and what the outcomes are. You have to have a consent form that the patients will be signing that has to be approved. You have to get approval by the Institutional Review Board. And then the hard part is finding a sponsor, getting funding and getting money to do your study. And then there's a lot of responsibility for the principal investigator. Overall, the principal investigator is responsible for everything. Everything from submitting the information to the FDA, to the IRB, to overseeing the nurse coordinators and the patient care. And then you have to register everything on the clinicaltrials.gov website. This is required if you want to publish your results. And it has to be registered before patient number 1 signs the consent form. If the patient signs the consent form and you have not yet completed and finalized the registration, you are not allowed to publish your data. So keep that in mind. So this is an example of a 1571 form, one of the ones that I filled out. And you have to put in this one, every time you send it in, you have to put your INT number in the little box, and then there's another little box for the serial number. So the first time you submit your application, your protocol, and you're getting approval, it's the serial number 0000. And then the next one that you send in, even if you're sending a report saying, I'm changing the protocol to this paragraph to the next paragraph, you have to submit the changes, and you put in here, what you're submitting in the report, down to the bottom, and then the next serial number will be 001 and then 002, etc. So you have to send it in sequence. And this, it's all now done electronically for the FDA, and you have to do this for every time you submit something to the FDA and communicate with them. The other thing that's really important with your research, before you take it to a clinical trial, or even before you go out and present a poster in that meeting, you have to make sure that you've secured intellectual property. So you may not have the patent yet, but if you have filed a provisional patent, which is very inexpensive, it's only a couple $100, the institutions will do that for you, it protects you. And so you should do that before you go out and present anything publicly, even at a poster session. So the other thing is that the patent belongs to whoever you're working for. So for me, I'm working for Georgetown, and I have a great discovery. They are the owners of the patent, because they pay my check. So but that's important. And if for some reason the university or the NIH or whatever chooses not to pursue your patent, they don't think that it's going to go anywhere, then inventors have the right to get that invention back and file it themselves. And I did that with one of my patents, which is now licensed and it's being approved by the FDA to treat Crohn's disease. So it's important that you stay on top of things. Finding a company, there's a lot of biotech companies out there, and they're probably easier to deal with than the big pharma, because big pharma likes their own ideas rather than dealing with universities, is my opinion. But then you want, when the patent comes out and it issued, you do want to license it to a company, because you can't do, once you're an investigator, you have to turn it over to a company so that they will develop it. They have the resources and they can do the multi-center trials. So that's important. But the very important thing about when you license your patent, you should have milestones in there for whatever company you're dealing with. And if the company does not reach their milestone and they don't develop your drug or your idea in the time frame that they're supposed to, there should be a clause that you get it back. Because there are companies that are out there that will take people's ideas and just set it on the shelf to kill the idea so that they can come up with a competitor. So that's very important. This is just one of the patents. This is what a patent looks like, and this is just one of my patents that issued in 2014. So the next thing you need to do is you need to write your protocol, and there's kind of an outline on how you have to do your protocol, everything from the title page to the summary. Usually you do an overview summary of the whole project, and then that's followed by the 100 and something page document of the entire protocol. And this is just one of my protocols. I'm just showing you some examples of things that we're working on. And you have to have, pointer's working. You put your protocol number there, you put the title of your protocol, if it has a number, you understand what critical stage it is. So this is the phase 1 and 2, how long it's going to be, what's the investigational drugs that you're using, what's your research hypothesis, and then you just spell out what's your primary, secondary objectives, what are you going to do by this study. So in this study we're doing a phase 1, and we're going to try to find out what the recommended phase 2 dose is by doing the phase 1, and then we're going to move into the phase 2 part of the study. And then of course you want to say how many centers are included, how many patients you're going to treat, inclusion, exclusion criteria, et cetera, et cetera. So that's how you have to do, that's the outline for your protocol, and what your drugs are and what the dose is, just kind of a summary, and then you go into detail in the protocol. So the aim of a phase 1 trial and first in human trial is really just look at the safety and toxicity, determine the maximum tolerated dose, look at any pharmacokinetics. And I did some work with a drug called OGF, opioid growth factor, and we're going to study the route of administration. But when we did this study, we used the typical dose escalation studies called the classic 3x3 design, where you enroll 3 people with 1 dose. And the dose you choose should be, you start off about 100 to 1,000-fold lower than the dose that you used to be in animals. So when I did this study the very first time, I knew that I had used a certain dose in my life, and so we used the lower dose. And the very first patient I gave it to ended up in the hospital in the emergency room that weekend. And I had to make a decision, was it my drug that made her get sick, or was it because she had metastatic pancreatic cancer? And so I went ahead and I enrolled the next 2 patients, and they did just fine. And so we escalated, we actually ended up going from the 50, from the 25 dose, all the way up to 250. So the patient actually had just gotten 60% of her cancer. So let's talk a little bit about some of the research that I do with pancreatic cancer and some of the clinical trials we're working on, and how you can take an idea from the bench to the bedside. Is anybody here working on pancreatic cancer? Nobody. Okay, yeah. Come on, I need some competition. Well, it's the 3rd leading cause of cancer-related death in the United States, about 53,000 people a year. And the median survival, unfortunately, is only 3 to 6 months, and only about 6% survive 5 years. This survival rate has not changed in the past 50 years. In spite of all of our technology, all of our PET scans, all of our diagnostics, all of our treatments, nothing has been effective. So the death rate from pancreatic cancer is actually increasing. And you can see over here that it's already surpassed colorectal cancer, and it's surpassing breast cancer, and it's going to be soon, second to lung cancer by 2020. So these are our current treatments for breast cancer with chemotherapy, and the one on the left is FOLFIRINOX that was compared to the standard of care gemcitabine, and they got a survival of about 11 months. But you can see, as you get down the numbers towards the end, there are very few patients still alive. Those are the number of patients. And then our other standard treatment is Gem/Abraxane, which is nab-paclitaxel compared to gemcitabine alone, and that can increase survival from 6 months up to about 8 months. So neither one of those, that's our standard. That's the best we're doing today, and neither one of them is even at 1 year. So why is the prognosis so poor with pancreatic cancer? Well, one of the problems is that 90% of the people who are diagnosed with pancreatic cancer has already spread beyond the pancreas. It's very metastatic, and because of that, they're not amenable to surgery. So we don't have any screening tests for patients who might be at high risk. We don't have, like with breast cancer, you can screen with mammography. We can't do screening colonoscopy type again for colorectal cancer. So there is no screening test, and the current CAT scans and MRIs are not sensitive enough to pick it up in the early stages. And it's also resistant to chemotherapy, and it's resistant to immunotherapy. Everything to be applied to pancreatic cancer with has failed. So my research, and Dr. Moody is an expert in this field, is on CPK or cholecystokinin receptors. And there are 3 types of CPK receptors. Easy to remember, A, B, and C. A was originally called A because it was discovered in the allometric tract, and B was originally discovered in the brain, and C is a receptor that we found as a slight variant that's only found in pancreatic cancer. So the CPK receptors are the class of G protein coupled receptors that have a 7-band membrane domain, and the CPK and gastrin are the major ligands for the receptor, and they have the same terminal pentapeptide, and that's how they combine to the same receptors with different affinities. So what is cholecystokinin? Just to refresh you with your physiology, this is the liver, that's the pancreas, that's the gallbladder. So whenever you eat, and especially whenever you eat something high in fat, free fatty acids and certain amino acids get into the second portion of the duodenum, and they stimulate the release of CPK from the eye cells in the duodenum. And CPK is a classic hormone, so it gets into the bloodstream and it circulates to the receptors in the pancreas, and it causes the pancreas to secrete digestive enzymes to help you digest your food. It also causes contraction of the gallbladder, so that the bile will help you emulsify your fat and digest your fat, and it causes relaxation of the sphincter of Oddi, so that the bile can come out and help you digest your food. Gastrin is the other peptide that binds to CPK receptors, and gastrin is made in the G cells of the antrum of the stomach. So the stomach is divided in half. You have the endocrine part of the stomach and the exocrine part of the stomach, and the G cells release gastrin, they get into the bloodstream, and they act on the enterochromatin cells, which also secrete histamine. If any of you are familiar with Pepsid AC or Zantac, any of those things, those are histamine blockers, H2 blockers, and they block acid by blocking the histamine. And then we have the proton pump inhibitors. So regardless of whatever is stimulating the parietal cell to secrete acid, whether it be the histamine, acetylcholine, or gastrin, the end result is the proton pump which secretes the acid. And so if you don't secrete the blockers with a proton pump inhibitor, like Liberal, Prilosec, Prednisone, Nexium, the little purple pill that everybody says is so good for their heartburn, the problem is that it blocks the normal feedback. So if gastrin is being, if the proton pump inhibitors are blocked here, gastrin levels will go up because you're not making enough acid. And when that goes up, one of the things that I see when I smoke these patients is you get all these polyps in the stomach. And these polyps are because the enterochromatin cells are stimulated, and gastrin is a perfect hormone, and it stimulates growth. So it stimulates growth, and in animal models it can cause carcinoid and gastric cancer. So we found that the CPK-D receptors are actually overexpressed in pancreatic cancer compared to normal cancer. And we found that if you treated cancer cells with gastrin or PTK, that it stimulates the growth in cell culture. So that's on the far right. And what we found when we looked at what type of receptor was on the cancer cells, we found that if we treated the cancer cells with gastrin, we could stimulate the growth, but if we added it with a CPK antagonist, it did nothing, then we could block the effect with a CPK-D receptor antagonist. So that let us know that even if the cancer cells have both A and D receptors, it's only the D receptor that's responsible for the growth. And then we showed also in animal models, if you treat the animals with gastrin, you can stimulate the growth of their pancreatic cancer, so you can block the effect with an antagonist, the gastrin receptor, or the D receptor. So we found that the gastrin and CPK-D receptor are actually turned on early in these precursor lesions called Pannin lesions in the pancreas. And a Pannin lesion is the same thing for pancreatic cancer as a polyp colon cancer. It's a precancerous lesion. And they get turned on very early, and it causes it to progress. So we stained these, we had some transgenic KRAS mutant mice that spontaneously with these Pannin lesions, and we showed that if we stained it for CPK-D receptors, that they were remarkably overexpressed in the mouse pancreas, which is really surprising because the mouse pancreas usually has the A receptors, but under the influence of KRAS, they make D receptors. So we took our transgenic KRAS mice, and we put them in the drinking water of PTK antagonist to block the receptor, and then after several months, we took the age-matched mice, and on the top, as you can see in the control mice, that their pancreas was completely replaced with these precancerous lesions and some early carcinoma, whereas the mouse that was on the CPK receptor antagonist therapy at the same age had very few, if any, of these lesions, and we had waited actually for the mice for 3 or 4 months before we started the treatment, because we wanted to make sure that they all had some tannins. This is an islet cell here in the pancreas. So with pancreatic cancer, we talk about tannins, which are the precancerous lesions, but they actually, if you put out the cancer, they only make up about 20% of the whole tumor, and the rest of the tumor is made up of stroma or fibrosis. And there's a lot of things that play a role in controlling the growth of pancreatic cancer, including that there's a lack of tumor infiltrating cells, and there's inhibitory T regulatory cells that suppress the normal immune system from fighting the pancreatic cancer. So there's a lack of the CD8 cells and an increase in the T regulatory cells. And then there's fibrosis. It's thought that that may prevent our chemotherapy from getting into the cancer. And there's some studies that show that the more fibrosis is there, the less people will respond to the chemotherapy. So this is a study done by Berta that showed that there are CPK receptors actually on the pancreatic stellate cells, and these are the fibroblasts that cause all that fibrosis of the microenvironment. And this was a picture we stained them for the CPK-D receptor, and they were positive. So we did a similar study in our mice, and we wanted to know if we put them on the CPK antagonist, can we block the fibrosis too? And indeed we did. So the blue stain is a Mason striped stain, and you can see that the age-matched mice, there's much less fibrosis because the CPK receptor antagonist blocks the fibrosis. And then the third cell that CPK receptors are found on are the immune cells. And the immune cells, meaning the lymphocytes, have both CPK-A and CPK-D receptors. And that's important because if the cancer progresses from normal to cancer on the far right there, the T cells, the T regulatory cells increase, and they suppress our own host immune system from fighting off the cancer, and the CD8 cells or the T killer cells decrease. So we did some studies, and a lot of research is changing. We used to do cancer studies in muted mice, but the problem is that these mice don't have T cells. And so if you're interested in looking at the immunity or what's going on in the microenvironment, you have to use a mouse with a normal immune system. And with all of our new immune checkpoint antibodies, you have to use an animal model that has an immune system. So they've been developing more and more animal models that are more similar to humans that have an intact immune system. So in our studies, we use C57 black cyst mice or our transgenic mice that have an intact immune system, so we can study immune checkpoint antibodies. So we consider one of the problems with pancreatic cancer is that it doesn't typically respond to immune therapy. And the reason it doesn't respond is because there's no CD8 cells in the tumor, or it's going to attack the tumor. And then also you have this fibrosis and the T regulatory cells in the microenvironment that prevent it from the immune checkpoint antibodies from working. So we came up with a hypothesis that if we treated pancreatic cancer with CPK receptor blockade, we could decrease the fibrosis and we could alter the immune signature of the microenvironment and make it more susceptible to immune checkpoint antibodies. And actually that's what we found. So these are animals who were getting TDS or the immune checkpoint or the antagonist by itself, but when we added them together as a combination, the tumors did not grow. And the reason they didn't grow, we looked at the inside of the tumor independently, and we found that the CD8 cells go up, so we have a combination of the immune checkpoint antibodies along with our CPK antagonist, and the T regulatory cells go down. We also showed that this improved survival of our mice, and that only the mice getting the combination therapy were alive at the end of the study. The other important finding was that we saw that only the CPK antagonist reversed the fibrosis, not the immune checkpoint antibodies. The immune checkpoint antibodies by themselves were not effective. So what we've done now, since we completed that in animals, we've actually designed a clinical trial to do the phase 1, phase 2 trial. And we're going to use our CPK receptor antagonist along with an immune checkpoint antibody. And we're going to do a pilot trial in patients. We're going to figure out what the maximum tolerated doses of our CPK antagonist. And we're going to work with a company that has already approved our protocol. And we're going to treat patients who have pancreatic cancer. So where we are right now, we secured intellectual property. We're getting the IND number. We have a source for our antagonist. I have an industry partner. And of course, I'm waiting for the funding, and hopefully that will come through. So now the other problem I mentioned with pancreatic cancer is that there's no biomarker, there's no way that we can screen patients that might be high risk. CAT scans, PET scans, MRIs are not sensitive enough, so what are we going to do? And are there any blood tests or anything that we can use to evaluate patients? So many years ago, when I was doing just a regular PCR trying to figure out what type of receptors pancreatic cancer had, I found that compared to normal pancreas, there was this bigger PCR product in some of our pancreatic cancer patients. You guys don't even discover them more, that's the block below that. But there was about a 200 base pair difference between pancreatic cancer and the CPK receptors in normal pancreas. And actually what we found out was that in up to 35 to 40% of patients who had pancreatic cancer, they had a single nucleotide polymorphism that caused a missplicing of the CPK-D receptor gene. And when this missplicing occurred, translated into protein. And so this correlates with the SNP that we found. And the reason why we couldn't do this in mice, and it never would have been found if we just were working with mice rather than human blood and tissue samples, was because in humans, the third enzyme has an open leading zone, but in mice and rats, there's a stop codon. So we could look all we wanted in our animal models, and we could never have found the splice variant. But we did find that there is the SNP. And the SNP is very important because it may predict who might be at risk of getting pancreatic cancer, similar to the BRCA2 with breast cancer, not the one with ovarian cancer. So the other important thing is that where this occurs is in the third intracellular loop. And what it does, that's the part of the CCK receptor that stimulates growth. And so we hypothesized that if they have this expertise, because the fourth intron is translated into protein, maybe people who have the SNP grow, or the cancers grow much faster and they have accelerated growth. We did make an antibody to our SNP protein that distinguishes it from the regular CCK receptor. And so we could image the cancer cells that have this genotype for the SNP, and they express the splice variant, or we call the CCK receptor. So we did a pilot trial, and we took 110 patients, and we took blood samples from them, and we confirmed it, with the opposite tissue samples, and then we saw that their survival was definitely affected if they had this SNP or not. So then we did a larger trial on over 1,000 patients to confirm our results. And so this is a validation trial, and that's another type of clinical trial that you can do once you do your pilot trial. And we did show that there was definitely a difference in survival in patients who had the SNP that didn't live as long. So we're hoping that now that we've identified the SNP in pancreatic cancer, by either doing a blood sample or doing a publicly posted swab, we might be able to identify people that are at high risk of getting pancreatic cancer. So the third problem is that chemotherapy is toxic and it doesn't specifically target pancreatic cancer. A lot of cancers, if you can identify a receptor on the surface for a cancer, whether it's HER2 or whether it's an estrogen receptor, then you can actually target your therapy. So there are no targets so far for pancreatic cancer, and there's also no imaging tests that have been effective in determining it early. So we decided we would develop a nanoparticle that would target the CCK receptor, and we call it a theranostic compound. So it's a therapeutic and it's a diagnostic compound. So what's a nanoparticle? And this kind of puts it in perspective. Nano means it's somewhere between 10 and 100 nanometers in size. And just to summarize why we use the CCK receptor as a target, if you look on the left, in a normal pancreas, there are some CCK receptors on the cell surface, and CCK or gastrin can bind to the receptor, and when they do that, they secrete the digestive enzymes. But in pancreatic cancer, cancer's not interested in digesting your food, the cancer's just interested in proliferate. So when the receptor is stimulated, the cancer cells grow. And then what happens is something turns on gastrin, and the gastrin starts being produced by the pancreatic cancer cell, so it stimulates its own growth by an autocrine mechanism. And then this little loop here is the splice variant CCK receptor, which is present in about 40% of patients. So we developed a couple different types of nanoparticles. One of them is the nanolipidome, one of them is the calcium phosphate nanoparticle, and we can design them so that they can carry siRNA, and it can knock down gastrin that's in the cancer, and we put the target on the outside so that it will bind specifically to the CCK receptor, and then we can also load these particles with either a fluorophore or magnetite so that we can identify it by imaging or with MRI. So we've also designed a special way that we can bind a DNA aptamer that we found by doing the Zelix method, and this aptamer binds selectively to the CCK receptor and does not stimulate growth. So we have taken this aptamer and we've covalently bound it down to nanoparticles, and so the nanoparticles will deliver whatever we want it to directly to the cancer, and they'll bind to the cancer, to the CCK receptor. This is just a picture of a couple of mice here on the left. These mice were injected with nanoparticles that had hydrogen green in them for fluorescence, and they were not targeted to the CCK receptor, and at 7 hours and 24 hours you can see that there's really nothing left. However, in the mouse that has orthotopic pancreatic cancer growing in its pancreas, where they were injected with the nanoparticles, with the targeted nanoparticles carrying the fluorophore, you can see at 7 hours and still 24 hours later, the particles are still concentrated in the tumor in the pancreas. So we've now designed a particle that will target selectively pancreatic cancer, and it can carry fluorophore, so we might be able to use this for early diagnosis and imaging in people who have small or early cancers. Another one of the nanoparticles that we've designed is called a complex mind cell, and it actually is made up with a polylysine tail, which is positively charged, and when we add it to our siRNA, it forms a mind cell, and we have our aptamer on the outside here, so it binds to the receptor. The siRNA is on the inside, so it's protected from the blood and does not degrade, and we have polyethylene glycol, so it doesn't conglomerate in the blood, and the blood cells don't take it up. So we've already done studies in mice where we show that if we can get this nanoparticle inside our cancer cells, we can actually deliver siRNA to gastrin to see if we can knock down gastrin, and we could knock it down by qRT-PCR, and we showed that the gastrin was also knocked down by peptide. And then when we treated our animals, only the animals that got the nanoparticles that were selected for the CCK receptor and carried the gastrin siRNA had decreased growth. So there's great potential for this platform that we can target whatever your receptor of choice is. It can carry whatever siRNA you want. If you want to knock down something, this can do it. Also, there are CCK receptors in other cancers like gastric cancer, colon cancer, medullary cancer, and some lung cancers. So we have a team of scientists, and we're hoping we apply to the ones AOC, our green team, Stand Up to Cancer. And again, to take something like this with our nanoparticle and take it to the clinic, it's going to take a whole team of scientists. I mean, I'm a clinician scientist. We have an oncologist working with me. We have somebody who's a material science engineer who helps design this. I have an imaging engineer, a pharmacologist, a toxicologist, project manager. So we have patient advocates to make sure that we're doing the right things and spending money wisely. So that's taking an idea. As we find out there's a problem, there's no way to diagnose pancreatic cancer in the early stage, so we're going to take down the receptor and we can target it. So what are the obstacles with saying regional research today? So of course the biggest obstacle is money. It costs money to take any project from the bench to the bedside. And if there are lack of funds, misuse of funds, disparity of funds, whatever, it takes a lot of money to develop these ideas. I'm a clinician scientist, and so I can say clinicians don't get protected time to do translational research. They would rather have me on the plate doing colonoscopies, but they think that makes more money, wants more people. But, in the long run, coming up with a cure or discovery for a cancer is, I think, much more important. So it's getting there, but doesn't pay as much as fast. There is a big division between industry, I think, and the NIH and academia. Industry likes to come up with their own ideas because they want to have the patent rights and everything. If you come up with an idea, you have to license it to the company and they have to pay you. So they would rather come up with their own. And of course, industry always comes up with what I call the Me Too drug. This is one different drug, but there's a Me Too drug that comes down, they're all the same, but they just modify it a little bit. So, and there's always problems getting patients to go into research studies. And if I can talk to Congress, I can tell them when they're coming up with a healthcare bill, they should tell people that if they enroll in a research study, they'll give them a discount, because that will get more people into research studies, and it'll help keep our costs down for healthcare, because it'll be covered by the research study. And of course, there's no more one-man band. You need a whole team of scientists to do a project. So, and the bottom line is, does the research really have any clinical relevance? These are a couple of my patients who, with their permission, when they show their pictures, they had failed standard chemotherapy for pancreatic cancer, and they enrolled in some of my research studies, and they're happy to talk about participating in research. And we need more patient advocates like this that will support research. And then what about our PTK antagonist? What's the potential side effect? Well, it might decrease heartburn. So I think that would be a beneficial side effect. There are PTK receptors, as we talked about, in the stomach. But if we deliver our gas and siRNA to those receptors, those cells don't make gases, so there won't be any harm. But our antagonist, if we block the receptor, we will probably have less acid. These drugs were actually developed 20 years or more ago to treat hepatitis disease. And with the advent of the proton pump inhibitors, they have fallen off the wayside, they're no longer under patent, and people have lost interest in them because the proton pump inhibitors are $1 billion business. And so people have forgotten about these drugs, so they might have another use. So you need to think about it when you're doing research too, by repurposing old drugs. They may be beneficial for another cause. I just want to thank some of my collaborators that helped with some of our research, and of course all of my animal volunteers. So I'm happy to take any questions. That's an excellent question. And there's a couple of possible hypotheses. One is the obesity and metabolic syndrome. High-fat diets. It's well known that in countries that consume high-fat diets, the incidence of pancreatic cancer is skyrocketing. We know that high-fat stimulates CPK. CPK binds to the CPK receptor, and that may stimulate the growth of pancreatic cancer. The other possibility, and although the industry doesn't want to hear me say this, is that for the past 20 years, when the incidence of pancreatic cancer has nearly quadrupled, also has the use of proton pump inhibitors. Proton pump inhibitors raise your gastric level, and we showed in our study that there's pre-cancerous regions in the pancreas, which everybody has them. Those kind of like people have pulse in their colon. We don't know what triggers them to go on to become carcinoma and fight against cancer. But we showed we could prevent that effect if we use the CPK antagonist to block the gastrin. So it's possible that the proton pump inhibitors that have been overly used and abused in the past 20 years are related to the increased incidence of pancreatic cancer. That's my thought. So, other questions?
Well, your clinical trial, will there be screening the patients first to make sure that they have issues?
Yes, we are. So patients will have biopsies before they start in the study, and also about 4 weeks into the study, because we're interested not only in the receptor density and how well they respond based upon their CPK receptor number, and also we want to look at the microenvironment too to see if our therapy will be increasing the influx of CD8 positive cells and maybe decreasing fibrosis. So we'll be doing a second biopsy in our clinical trial. And that leads to our better understanding of what's going on in humans. I mean, we know it happens in mice, but we want to know if it's going to happen in humans. Yes. A transfected cell line with CPK receptors. So all pancreatic cancer cell lines that we've screened and all pancreatic cancers from the operating room that we've screened all have CPK receptors. So we did not have to overexpress it at all in our cancer cells. In the animal that I showed up there that we did the binding, it actually was ESPT3, which actually doesn't have as many receptors as like PANC1, which is another pancreatic cancer cell line for APTC that everybody uses. We do, now that we're doing syngeneic models in immune competent mice, we're using some cell lines that are called MP3, MP5 cell lines that are derived from organoids from David Peterson's lab at Princeton Harbor. And he took the cells from these cannons and the cancers that developed from the KRAS mutant mouse, and he grew them as organoids and developed cell cultures, and he could put them back into the mice. And they resemble the human cancer very well because they have mutant KRAS, and they also overexpress GTKD receptors, and they make gastrin, which others will not. So they're a good model to use when you're doing immune competent mice. Yes. So the longer-term survivors here, the people who had the SNP all died rapidly. So if pancreatic cancer, whether you have the SNP or don't have the SNP, is still a poor prognosis. There are some longer-term survival patients, and at least in our study, the ones that survived longer had the wild-type genotype, the CC genotype, rather than the heterozygote AC or the AA, which is the SNP. So it may be related to it. And when we did our study, the statistician, who I support to have a statistician in our team, he evaluated all the data and made sure that we corrected for stage of disease, so that we were sure that the survival was not influenced by somebody with longer because they were early stage disease. So they corrected for all of those factors. So it may be related to that, yes. Thank you very much.
in terms of announcements, next week we don't have plans. Our next class will be 2 weeks from today. And let's see, quote unquote. He got his MD degree from the University of Kansas and did a residency at UCLA. And he won numerous awards. I saw him with the ACR Princess Takamatsu Award, where he spoke before most of the people came excellent on. And he's published over 500 journal articles. His claim to fame, though, is the editor-in-chief of the journal Parthenogenesis. So he's going to talk to us today about lung cancer, precision medicine strategy. Here. Okay. So I think you'll give you a very nice presentation about pancreatic cancer and how to do clinical trials. And I'm going to be talking about precision medicine. And then I'll use some examples of lung cancer to illustrate the current strategies of precision medicine, including the NCI Precision Cancer Initiative. So, yep, that's it. We all need them. Fantastic. Right. So, what I was going through, this is what I learned. This is traditional medicine, lifestyle, medical history, science symptoms, reaction from our hands on patients, and physical exam, and various simple laboratory tests and chest x-rays, things like that. So, precision medicine is different. It's multi-layered, it's individual-centric, and it's interconnected. That uses information content and these various links which I'll be talking about. So, the idea of precision medicine follows various strategies, systems called personalized medicine, deep-born medicine, and so on and so forth. But this was from a NCI, it was from a National Academy of Science report in which there was information comment that utilizes various holdings that's on the foundation of clinical information and ecological information. This leads to information or knowledge network and better classification of data. And this for the objective of improving clinical medicine. And these observational studies go back to the information comments to improve the process. It also informs the biomedical research that most of us do here as scientists. And there's the informed mechanistic studies also go back to information comments. That wasn't part of the proposal, but actually Marcus and I wrote an extensive review on precision medicine and prevention research. So let's first describe some clinical and epidemiological data. And as I said, I'm going to be focusing on lung cancer. And this comes from a report of the Surgeon General in 2014 that I and John Sanders and other people contributed to. And this is the 50th anniversary date of the smoking and anti-smoking campaign and starting it. And these are the number of individuals who had premature deaths as calculated by smoking or exposure to secondhand smoke for this 50-year period. The smoke before was late in people. And these are the smoking-related cancers and also the cancers from secondhand smoke and then other causes of death related to smoking. You're probably familiar with this kind of chart in which these are the cancers per 100,000 of the population, year of diagnosis. This goes to about 2014 or so. And male cancer, lung cancer, reached the peak, and it's rapidly falling. It's about almost not quite half of what it was. And the female cancer, lung cancer, is plateaued off and maybe starting to decrease. So smoking, in the United States, this is the amount of cigarettes in terms of smoking as a percentage. And this is obviously the U.S. It used to be like that, in which over 35% of the population was smoking. There's still populations in the United States in which there's high levels, especially in the world, in which there's high levels of smoking. So lung cancer is increasing in the United States and decreasing in the United States due to anti-smoking efforts that not in many other parts of the world. Now, not only active smoking, but passive smoking can increase the risk of lung cancer. And this is a watercolor that was actually done by Hirayama, an epidemiologist in Japan. And this was a meeting in 1981, which I and other people attended at Gates in Greece. And he presented for the first time that wives of Japanese workers disclosed had an increased risk of lung cancer. I will tell you at that time, the vast majority of people didn't believe it. And but he proved to be right. And now 50, 80 studies traditionally show that being around people who smoke or being exposed to smoke increases your risk of developing lung cancer. And this is a quotation from Hippocrates. I don't like these types of things, so bear with me. Some men, he was a famous to the women in those days, some men and women, I will say, had constitutions that were like wooded mountains, running like springs, others like those that pour soil and little water, still others like land rich in pastures and marshes, and yet others like the fair earth of the plains. Separated people different from one another in terms of constitution and risk of disease. So 28 years later, we decided to do a study of lung cancer in never smokers. And I had this idea while I was sitting listening to Hirayama give his talk, and that is there an increased risk of smoking in kids who were never smokers that were exposed to the smoke. And we didn't do this until 28 years later because the United States women didn't start smoking successfully until the second World War. And so we had to wait until 50, 60 years later that lung cancer occurs. And this is Susan who did this epidemiological study with us. At the time. And the conclusions from the studies of parental secondhand smoke exposure during childhood is associated with a dose-dependent increase of lung cancer risk among never smokers in two separate cohorts. And it's very important to look at multiple cohorts when you're doing these kinds of studies. And I think Jill makes that point too. And this was the increased risk of lung cancer was especially true with those that was finding lectin appetite with a hyperactive innate immune system, so inflammation and increasing risk. Probably surprising to us at the time that these people had lung cancer in their 40s and 50s, and not in the 60s or 70s that most cancer patients suffered through active smoking. So lung cancer is number one worldwide in terms of mortality and our group. I've had a slide before that was the department, as you guys know here. I'm studying primary lung cancer, Ronald B. Bryan, liver cancer is Jim Long, pancreatic cancer is Fred Hussein, and Stepanov is studying breast and prostate cancer. So we're studying the major worldwide cancers. And throughout the talk, now I'll be talking about early stage cancer and early stage lung cancer, because that's the opportunity to get the highest cure rates. But there's certain aspects of this that are important in terms of developing risk biomarkers to identify people for priority for low-dose CT, that's computerized tomography, and also their diagnosis, because many of these lesions that are detected by low-dose CT are benign. They need to know whether it's cancer or not. If there's a diagnosis of cancer and it's a surgical resection, one needs to know whether or not the patient is at high risk for recurrence, and if so, they might benefit from adjuvant therapy, either immunotherapy or chemotherapy. So let's first go to exposure and extensosome, as it's called. And this was coined by Chris Wild, who's the head of the International Agency for Research on Cancer, and it includes not only the external environment, such as tobacco smoke, infections, and diet, and so on and so forth, but the internal environment that's directly connected, such as obesity, which Joe mentioned also pancreatic cancer and heart inflammation. And these together can lead to cancer biomarkers of risk and diagnosis, cancer genome and epigenome, genetic susceptibility, driver genes, obviously for cancer therapy, but understanding carcinogenesis can also benefit our biomarker studies for cancer prevention and screening strategies. So let's talk about inflammation first. Inflammation can be largely inherited more than acquired. Conditions such as hemochromatosis, which is a higher glomerular disease, increased risk of liver cancer, or inflammatory bowel disease, or even pancreatic cancer. So that is associated with familial pancreatitis. So more often it's acquired, and it can be due to viruses, bacteria, and parasitic conditions. And I also like to point out human papillomavirus, because John Skiller and Ben Lowy just received the last award, one of the highest awards in medical science, just recently. A infection are chemical, physical, and metabolic conditions such as acid reflux, Barrett's esophagus, obesity, or smoking at multiple sites. And the global impact in the World Cancer Report that we put together in 2014 is about 2 million cancers per year are related to infection, and other causes of inflammation are associated with many more cancers per year. Smoking, for example, over 6 million cancers per year. To go further into inflammation, and these are a series of studies that we have done, and published on lung cancer, including looking at health disparities compared to African Americans to European Americans. And the first was a prospective study that involved about 100,000 people, and we found that in a tested patient control study that IL-8 and CRP, that's in European Americans, increased the risk of lung cancer. At the time of diagnosis, there was also continued increase in IL-8 and IL-6, but now we had enough cases to look at both African Americans and European Americans, and the African Americans had, other than these two, they had increased in movement beta and IL-10, which is an anti-inflammatory cytokine. And for survival, the inflammation also is related to the survival in case of lung cancer patients. This is again for the various other things that are important. So again, IL-6 and IL-8 increase the risk of dying, and anaphylaxis lectin that I talked about a moment ago increase in and alpha in European Americans, and again, IL-10 and IL-12 in this case in African Americans. So I mentioned IL-6 and IL-8, and this is the early stage of lung